guys are short in the wire itself, because if I move the wire, it makes it turn purple. Okay, so let's go ahead and see if we can prove this. What's the hypothesis? Well, yeah, let A be an ordered integral domain and all of that, up to the then statement. Okay, so the only thing that we can use on this one is the definition that they give us here. If you go back to page 209 in your textbook, it gives you the definition for an ordered integral domain. Notice that our definition for ordered integral domain on 2, 3, and 4, does it have any less than or equal to's, or all those strict inequalities? They're all strict inequalities. So if we're going to apply the definition, we have to break this up. Since it's an ordered integral domain, we know that it's either A equals to B or A is less than B. Now, if we go with the case, so assume that A is less than B, and we'll do the case when A is equal to B. Instead of saying assume, I'll say if A is less than B, then is there one of the cases, 2, 3, or 4, that helps us? Yeah. Then by case 3 in the definition, we see that A plus C is less than B plus C. What that tells us then is that A plus C is less than or equal to B plus C. If you look at the very end of the definition, they put the inequality in the paragraph following the second paragraph after the definition. They tell you what that means. So I can say that A plus C is less than or equal to B plus C in that case. Now, if A equals to B, what do we know?
And that one, would we be putting less than or equal to? Or is it just strictly less than?
Don't we have to show both and then?
No, I'm going to actually arrive at the same conclusion in both cases. I'm doing kind of two cases, so maybe I should break this out. So, case if A is less than B, and then we can have another case here if A equals to B. So in both cases, I have to arrive at my less than or equal to. I have to be able to get that less than or equal to in there. Yeah.
I don't see in the book how you're able to go from A plus C less than B plus C to that from what the book says.
The book says one or the other happens. So if you have an or statement, A or B happens. And if I guarantee that A happened, then you know that you're whatever, if this meant A star B. If A star B means A or B happens, and I know that A happened, then that tells you that your relationship happened.
Okay.
Okay? So in my relationship here, I have one thing. A plus C is less than B plus C. So it's less than or equal
You
to.
can say this, okay.
Yeah, because it's the or relationship. Okay, so if A equals to B, tell me about A plus C and B plus C. Equals. Yeah, you changed anything on either side, so you know that A plus C equals B plus C. What does that tell you then? A plus C is less than or equal to B plus C, because you have one of your or conditions satisfied. And so, in both cases, we see that A plus C is less than or equal to B plus C, as desired. Now, you guys are doing A number 1. That one's a little bit trickier, so go ahead and And try that, that's actually the transitive property for inequalities. But you're gonna have to make an argument, again, split it up into your two cases, but it actually ends up being 4 cases for you. Because you have 2 inequalities that could break down into 2 options, and you have to go through all 4 options. Other than that, it's straight the same way that we just did right here. So go ahead and attempt that. How do you show unique? How do you show something is unique? Assume 2 and show they're equal. That's always the method you're going to do to show unique. So let's get our hypothesis. Let m and n be integers. And are they positive integers? If m and n are integers and n is positive, now here we're going to assume that there's 2 sets of these q's and r's, so let's call them q1 and r1 and q2 and r2. Assume that there exists q1, r1, I want commas in here, q2 and r2, and I forgot the commas again. And these are also going to be where? In the integers, right? And they satisfy our division algorithm. M is equal to nq1 plus r1. And what's the property on r1? Yeah, 0 is less than or equal to r1 is less than n. And m is equal to n q2 plus r2, again, where 0 is less than or equal to r2 is less than n. Now they're both equal to m, so what do you think we should do? Set them equal to each other, So we're going to have the first one equals to the second one. Now, what do you think we should do from that? Yeah, get the q's on one side and the r's on the other, the q's and n's on one side. So if we do that, we combine it, I'd have q1 minus q2, right, is equal to r2 minus r1. Our whole goal, it would be really nice if we could show that r2 minus r1 equals to 0, or that q2 minus q1 equals to 0. That's what we're trying to do. What do we know about r2 and r1? They're between 0 and n. So what can we say then about r2 minus r1? Well, r2 is going to be less than what? Yeah. So this is going to be less than, well, in fact, strictly less than n minus r1. But what do I know about r1? It's smaller than n. So that should be something smaller than what value? Someone has actually said this. Can I go straight to n? Does that make sense to you guys? All I did on the first one, looking at subtraction here, so I know that r2 is smaller than n. So I just replaced it by n. So n minus r1. But r1 is between 0 and n. So n minus r1, if this, the biggest value n minus r1 can be is n, if r1 is equal to 0. So we get up to n. So r2 minus r1 is smaller than n. I'm going to put that on a different line here. by restrictions on R1 and R2. So go back and look at what we have our equality right here. I'm going to call this equation 1. Okay, so look at equation 1. It's kind of entertaining. We have n times some integer is equal to some value smaller than n. If I knew this value over here was positive, then I'd have my contradiction. I'd have to say it's 0. If I knew that I know it's smaller than n, but if I knew it was bigger than or equal to 0, then the only option I could have is 0 here, because you can't have an integer multiple of n be something between 0 and n, a positive value between 0 and n. You guys see that? You take 3. You do an integer multiple of 3. Can you get 2 for that integer multiple of 3? It's not going to happen. So we have to figure out some way to say that this value over here is greater than or equal to 0. I'm going to add one added restriction to all of this, and it's not really anything that's going to give us a problem. And that's this. Up here I'm going to say, assume, without loss of generality, that, let's see, R2 is going to be greater than or equal to R1. If that is not the case, then just switch the order of your subtraction. R2 is either greater than or equal to R1 or strictly less than R1. So if it's not the case, switch the order, and you'll still get the same work. So as soon as I do that, then I know that R2 minus R1 is greater than or equal to 0. So what does that tell us then? And so we see from equation 1, I'll just put it in parentheses, that R2 minus R1 has to be equal to what? An integer multiple of n. So if R2 minus R1 equals to 0, what can we say about R2 and R1? Yeah, R2 is equal to R1. Oh, got a minus in there. But equals R1. And so then we have n q1 minus q2 has to be equal to 0. But if n times q1 minus q2 equals to 0, and since the integers are an integral domain, n is not equal to 0. It was a positive integer. So what does that tell you about q1 minus q2? Yeah, it has to be equal to 0. So I have q1 equals to q2. Therefore, q and r are unique. In the division algorithm. There's uniqueness. It wouldn't have taken them that much longer to put that in there. I don't know why they didn't, but they didn't. Yes. left reader, yes, they wanted to leave you something to do. Yeah. Okay, so there's the uniqueness part for the division algorithm. And then, let me see what the homework was, because we were going to work the rest of the time on homework. Specifically, part D. You have to do D numbers 1, 2, and 3. The hardest part on that one is going to be part 2, because that was showing injective and surjective. That means you have to show 1 to 1 and on 2, which is the longest time period back from what we've done. So I would spend some time working on part D. The last homework problem is just straight, pure induction. So you should be able to do that one.
Injective is 1 to 1, surjective is not 2.
Yes. Mm-hmm.
What's the last time?
G1. Mm-hmm.
Injective
So doing A1, A1, 2, 3.
Uh-huh. Yeah. And in your part D, you're going to be using the methods that they used in proving. That's where they have their least positive, the well-ordering property on 210, where they kind of hid those proofs in the paragraphs in there. I think it's that first one dealing with an integral system. Yeah, showing that you don't have any values between 0 and 1.
Just so I know if I'm assuming it's wrong.
And the second one too, they're both the same type of idea.
For D1, the characteristic is not 0, is it? Because...
Yeah, it is 0.
Oh.
Because it's infinite. You're actually going to show that n times 1 is greater than 0 for every integer n.
How do you show that that was just such common sense?
Induction. Really easy induction
Because you're
proof.
showing that 1 plus 1 plus 1 is 0 on
Yes, on the integers. Well, this is an integral system. We're not proving that you're starting with a, so you don't necessarily know it's the integers, but you're doing 1 sub a plus 1 sub a and so on. So,
That's still the whole...